Hello everyone and welcome back to Linear Algebra with Python stroke Numpy, and this section will be looking at matrices. Okay, so now in today's video we are going to be talking about types of matrices. My name is George B. Smith. Sorry about that. Okay, so we're going to be talking about matrices, types of matrices to be precise. So in a couple of videos back we've already looked at some types of matrices. We talked about the square matrix, we talked about the vector matrix, the non-square matrix, and then we looked at two types of vector matrices. So in this video we are going to look at some other types of matrices. Okay, first we'll start with the diagonal matrix. Now what do we actually mean by diagonal matrix? Now when you talk about a diagonal matrix, you're looking at the matrix, but to start with it must be a square matrix. So you're looking at a square matrix that has all of its elements to be zeros except the elements of the principal diagonal. Okay, so the principal diagonal, this is what we have. This is an example. This is what you call the principal diagonal here. The diagonal that runs for a square matrix, the diagonal that runs from the top left down to the bottom right is what you call the principal diagonal. So when you have all values to be 0 except the values you have here, then you call that a diagonal matrix. So this I have here is a 2 by 2 diagonal matrix. We have another example. This is what you call a 3 by 3 diagonal matrix. So they must be square matrices. That's number one criteria for something to be a diagonal matrix. First must be a square matrix, then all elements should be 0 except at least one element of the principal diagonal. So there is a possibility of this being 0 and this being 0, but this being a value. It's still a diagonal matrix because you have at least one element there being a non-zero value. Okay, so these two matrices we have here, they are called. So here also, this is what you call the principal diagonal. We give them different name. If you've gone through the other videos, you must have seen it. We call them principal diagonal, leading diagonal, or primary diagonal, from the top left down to the bottom right. Okay, so we have one more example. This is another example. Now this is also a diagonal matrix, but this diagonal matrix would now lead us to the next type of matrices. Now if you look at the difference between this diagonal matrix we have and this other one, say, you notice that this matrix, it being diagonal, yeah, it's quite obvious that it's diagonal, but if you also look at it very well, the element of the diagonals, they are the same value. It could be 5 5, 7 7, 10 10. If they are all the same thing, that leads us to the next type of matrix that we call a scalar matrix. So in general, scalar matrices are also square matrices, so you can say they are diagonal matrices in which the elements of the leading diagonal are all equal. So when they are all equal, you call that the scalar matrix. An example is what you have here, the one we had in the previous slide, and then you have this another example, and you have this as another example of scalar matrices. Okay, so you can put it this way, that all scalar matrices are diagonal matrices, but not all diagonal matrices are scalar matrices, because if you notice, this we have this first two, A and B, they are diagonal matrices, but they aren't scalar matrices. Okay, so every scalar matrix is diagonal matrix, but not all diagonal matrix is scalar matrix. Okay, so next we have this other example. This one here is also a scalar matrix, but this is still going to lead us to the next type of matrix. Now you notice that these elements are still the same like all scalar matrices, but here they are both equal to 1. So when they are both equal, when all the elements of the principal diagonal are all equal to 1, that leads us to the next type of matrix that we call the identity matrix, also called the unit matrix. Okay, so unit matrices have every element to be 0, or they are diagonal matrices in which the elements of the principal diagonal are all 0. So this is called order 2 diagonal matrix. This is order 2, this is order 3, sorry, unit matrix, and this is order 4 unit matrix. So all these ones we have here, they are all units or identity matrices. Then we have the triangular matrix. A triangular matrix is also a square matrix. This time around it has all elements below or above the principal diagonal to be 0. So you can see This is the principal diagonal. Here we have elements below to be 0, or you can have elements above. Again, this is the principal diagonal. Okay, we have this as the principal diagonal. You have the element above to be 0, so they are saying the element below or the element above should be 0. So here also you can see that this is the principal diagonal, the element below are 0. So these are what you call triangular matrices. So triangular matrices, they are of two kinds. We have what we call the lower triangular matrix, and we have what we call the upper triangular matrix. Now the difference between this lower and upper triangular matrix is that for a lower triangular matrix, you're looking at a case where the triangle falls in the lower. Don't mind this, my writing. Shit, sorry about that. Okay, so this we have is an example of upper triangular matrix, because the triangle is formed at the top. So when you have the element below to be 0, you have upper triangular matrix. When you have the element above to be 0, you have a lower triangular. So this is a lower triangular matrix, this is upper triangular matrix. Okay, so we have two types of triangular matrices, the lower and the upper triangular matrices. Okay, so next we have a symmetric matrix. So for symmetric matrices, you are looking at a matrix where when you look for the transpose, we'll come to the transpose of that matrix, it's still going to be the same thing. Okay, let's see what I have. I have a matrix A. Okay, this is a matrix A. This matrix is going to be a symmetric matrix if when I transpose A, when you transpose A, this is what you're going to get. A superscript C. When you transpose A, you're still getting back A. This is what you call a symmetric matrix. So a matrix is symmetric if its transpose is equal to the matrix itself. So these are examples of symmetric matrices. How do you transpose a matrix? You transpose a matrix by making a row to be a column. We'll talk about the transpose of the matrix later on, but note that when I transpose this matrix, that means if I make the first row to become the first column, make the second row to become the second column, I'm still going to get the same matrix. So this is a symmetric matrix. This is another example of a symmetric matrix, okay? Because when I transpose this, I'm still going to get the same thing, and this is an example of a symmetric matrix also. So let me show you this one. If I transpose this matrix, so if I look for A transpose, so for me to look for A transpose, I'll make the first row, this is the first row, I'll make it the first column. So I'll take that first row minus 3. Okay, this is 7, but instead of the 7 here, I'll bring it down here. So that's the first row. I'll make the second column, the second row I have 7, then I'll bring this other one down here. You can see I've transposed this matrix, but it's as though I'm getting the same thing. So that's what you call a symmetric matrix, when the transpose is equal to the matrix itself. We are going to look at transpose of matrix in full details, and then you understand this symmetric matrix itself. But just note that for a symmetric matrix, A transpose is equal to A. Okay, when A transpose is equal to A, that matrix is called a symmetric matrix. Now, apart from identifying it with a transpose, one other way you can identify a symmetric matrix is to note that if I pick a particular element, Aij, okay, that it would be the same thing as me picking another element, Aj. For example, if I look for A31, it must be the same thing as A13. So what's A31 here? A31 row 3 column 1 is this, right? This is A31. There was A13 row 1 column 3 is this. So you can say A31 and A13, they are the same. So when you look for all cases, okay, where you have it as for all cases, this is for all, this symbol is for all. For all cases, the Aij and the Aji, they are the same thing. That matrix becomes a symmetric matrix. So that's it, guys. We are going to end this video here. In the next video we are going to start with skew symmetric matrix, which is similar to the symmetric matrix with a slight modification. We'll also talk about the dense, the sparse matrix, the singular matrix, and that's going to be it for the types of matrix. We have other types of matrices, quite alright, but that's where we're going to end it. We'll discuss other types of matrices later on, okay, as we proceed later in the course. So don't forget, guys, to like and subscribe to my channel, to click on the bell icon so that I get notified whenever I upload new videos. Okay, so I'll see you guys in the next video. Bye bye.